What exactly lies at the edge of the observable universe has remained a mystery for centuries, fueling curiosity and speculation among scientists and enthusiasts alike. However, the James Webb Space Telescope holds the key to unveiling this cosmic mystery. With its powerful lenses peering deeper into space, it has recently made a groundbreaking announcement about what lies at the edge of the observable universe. When we talk about the edge of the universe, it's essential to understand the concept of the observable universe. The observable universe includes everything that we can see, measure, and study from Earth or our space-based telescopes and exploratory probes. At present, it consists of stars, galaxies, and other celestial objects that are within our observational reach. So, what's the difference between the universe with a capital U and the observable universe? In simple terms, the observable universe is just a small fraction of the entire universe that we can study and comprehend. While the complete size and shape of the entire universe are unknown, there is an estimated diameter of the observable universe, which is around 93 billion light-years. A light-year is a unit of distance that light travels in 1 year, which is about 5.88 trillion miles or 9.46 trillion kilometers. So, the diameter of the observable universe, 93 billion light-years, is an unimaginably vast expanse, spanning approximately 54,684,568.58 billion trillion kilometers, showcasing the mind-boggling scale of our cosmic surroundings that's difficult to even comprehend. But why is the universe so incredibly vast? The answer lies in its origins. The Big Bang Theory tells us that approximately 13.8 billion years ago, the universe was born in a powerful explosion. This explosive event triggered rapid expansion, and since then, the universe has been expanding at an increasingly faster pace, driven by enigmatic forces like dark energy. As the universe expanded, particles of matter started clustering together due to the force of gravity, forming structures such as stars, galaxies, and eventually even planets like our beloved Earth. Over countless years, these cosmic structures grew larger and more intricate, leading to the extraordinary diversity of objects and phenomena that we observe throughout the universe today. Despite the vastness of the universe, it is predominantly empty. To put it in perspective, if we scale down our entire solar system to the size of a quarter, the nearest star would still be the distance of 2 soccer fields away. And this is just within our Milky Way galaxy, which is one among billions in the observable universe. You may wonder why we can't see the entire universe. There are 2 factors that explain this. The first reason is that light takes time to travel through space. When we look at distant objects in the universe, we're actually observing them as they were in the past. The farther away an object is, the longer its light has taken to reach us. So, by observing distant galaxies, we're essentially peering back in time, unraveling the history of our cosmos. The second reason is the universe's expansion. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move away from each other. The same principle applies to the universe, where galaxies are drifting apart as space itself stretches. This expansion causes the light from distant objects to become stretched too, shifting towards longer wavelengths, which we perceive as redshift. Eventually, some objects will move beyond our observational reach as they recede beyond a certain distance. Considering these factors, it's not surprising that we haven't seen the entire universe yet. Now, the concept of the edge of the universe is a mind-boggling topic that has fascinated scientists, philosophers, and thinkers for ages. We have all sorts of theories about what lies beyond, but the truth remains elusive. However, there are 3 theories that stand out. The first theory is that the universe goes on forever with no end in sight. This theory is based on the cosmological principle, which states that the universe is isotropic, meaning that it looks roughly the same in every direction. If this principle holds true, it implies that the universe stretches on endlessly without a boundary. The second theory suggests that the universe is finite, but it doesn't have a clear edge either. This means it's similar to a giant ball, and if you keep going in any direction, you'll eventually loop back to where you started. The third theory is the multiverse theory, which suggests that our universe is just one of many. Imagine a bunch of parallel universes, each with its own set of rules and properties. These universes could be completely separate from each other or somehow connected. So, we've talked about concepts surrounding the edge of the universe by looking at diverse theories. Now, let's turn our attention to a remarkable tool that holds the potential to shed light on these mysteries, the James Webb Space Telescope, JWST. This incredible telescope allows us to look far back in time and discover unexpected objects from the early days of the cosmos. The JWST, with its advanced capabilities, has enabled astronomers to peer back into the early days of the universe. And guess what? They've stumbled upon something unexpected. In a recent study published in the journal Nature, the JWST discovered 6 massive galaxies that existed between 500 million and 700 million years after the Big Bang. Researchers were only expecting to find small, newly formed galaxies, but the JWST caught them by surprise. These galaxies are way larger than anyone ever imagined, challenging what we thought we knew about the early cosmos. But that's not all. Scientists also found something mind-boggling. These galaxies are as mature as our 13-billion-year-old Milky Way galaxy. The mass of stars within each of these objects totals several billion times larger than that of our Sun. According to the research, one of them, in particular, might be as much as 100 billion times our Sun's mass. For comparison, the Milky Way contains a mass of stars equivalent to roughly 60 billion suns. You see, this telescope has a special power. It can see things that are invisible to our eyes by using infrared light. It picks up the faint glow from old stars and galaxies that have been around for ages. This means the JWST can literally take us back in time, providing a glimpse of what the universe looked like around 13.5 billion years ago. Certainly, here's a more detailed and expanded version. What lies at the edge of the observable universe has been a tantalizing mystery that has captivated scientists and enthusiasts alike for centuries. The James Webb Space Telescope, JWST, poised as humanity's next great eye on the cosmos, stands ready to unravel these cosmic enigmas. Equipped with powerful infrared detectors, the JWST represents a quantum leap forward in our ability to peer deeper into space than ever before, promising to reveal unprecedented details about what lies at the outskirts of our observational horizon. To grasp the concept of the edge of the universe, it's essential to first understand the notion of the observable universe. This is the portion of the universe that we can see, measure, and study from Earth or our space-based observatories. It encompasses all the stars, galaxies, and other celestial objects whose light has had enough time to reach us since the beginning of the universe. The observable universe, however, represents only a fraction of the entire universe, denoted as the universe with a capital U. Estimates place the diameter of the observable universe at about 93 billion light-years. This immense scale is difficult to fathom. A light-year, the distance light travels in 1 year, equals about 5.88 trillion miles or 9.46 trillion kilometers. Therefore, the diameter of the observable universe spans approximately 54,684,568.58 billion trillion kilometers. The roots of this vastness trace back to the Big Bang, the explosive event that birthed the universe approximately 13.8 billion years ago. In its infancy, the universe underwent rapid expansion, a process known as cosmic inflation, which has continued ever since. This expansion, driven by mysterious forces like dark energy, has caused galaxies and other cosmic structures to move apart from each other. Over time, gravity has led to the formation of clusters of matter, eventually forming galaxies, stars, and even planets. Despite the enormity of the observable universe, it is predominantly empty. If we were to scale down our entire solar system to the size of a quarter, the nearest star would still be about 2 soccer fields away. This vast emptiness is punctuated by galaxies, which are themselves vast collections of stars, gas, dust, and dark matter. However, our view of the universe is limited by 2 main factors. First, light takes time to travel through space. When we observe distant objects, we are actually seeing them as they appeared in the distant past. The farther an object is, the longer its light takes to reach us, allowing us to peer back in time and witness the evolution of galaxies and other celestial structures. Secondly, the universe itself is expanding. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move farther apart from each other. Similarly, galaxies are receding from each other as the fabric of space itself stretches. This expansion causes the light from distant objects to become stretched as well, shifting towards longer wavelengths, a phenomenon known as redshift. Over time, some objects may move beyond our observational reach as they recede beyond a certain distance. The concept of the edge of the universe has spurred numerous theories and debates among scientists, philosophers, and thinkers. One prevailing theory posits that the universe stretches infinitely into space without any discernible boundary. This idea aligns with the cosmological principle, which suggests that the universe appears roughly the same in all directions, isotropic. If true, this theory implies an endless expanse of cosmic wonder stretching beyond our current observational limits. Another theory proposes that the universe is finite but lacks a clear edge. Instead, it resembles a vast curved space akin to a giant ball. In this scenario, traveling in any direction could eventually bring one back to their starting point, similar to circumnavigating the globe on Earth. A more speculative theory, the multiverse hypothesis, suggests that our universe is just one of many universes existing alongside each other. These parallel universes may have different physical laws and properties, potentially interconnected or entirely separate from each other. Amidst these theories and speculations, the James Webb Space Telescope, JWST, emerges as a beacon of hope for shedding light on these profound cosmic mysteries. By peering deeper into space and farther back in time than ever before, JWST has the capability to observe the early epochs of galaxy formation, trace the evolution of stars and planetary systems, and delve into the nature of dark matter and dark energy. Already, JWST has begun to make significant discoveries, unveiling ancient galaxies that formed in the universe's infancy and shedding light on the conditions that gave rise to our cosmic neighborhood. Its advanced instruments and unprecedented sensitivity enable astronomers to study celestial phenomena with unparalleled detail, offering glimpses into the very fabric of our universe. As JWST continues its mission, it holds the promise of revolutionizing our understanding of the cosmos, pushing the boundaries of human knowledge, and inspiring new generations to contemplate the vastness, complexity, and beauty of our universe. With each observation, JWST brings us closer to answering age-old questions about our place in the cosmos and the mysteries that lie beyond the observable universe's edge. By peering deeper into the universe than ever before, JWST reveals stunning details about the early universe and distant cosmic phenomena. By capturing faint infrared signals, JWST has detected galaxies that formed shortly after the Big Bang, offering crucial insights into how the universe evolved over billions of years. Its unprecedented sensitivity and resolution have also allowed astronomers to study planetary systems in formation, uncovering the building blocks of worlds potentially similar to our own. Moreover, JWST's observations contribute to our understanding of dark matter and dark energy, fundamental yet enigmatic components shaping the cosmos. As JWST continues its mission, it promises to unlock more mysteries at the cosmic frontier, pushing the boundaries of human knowledge and inspiring awe and wonder about the vast